we are very happy to have Dr. Wandu from UC Merced. So actually, he fly all the way from California here, so that to come to visit us. His research is fantastic. As you can see from the, I know him quite a lot. Am I also your mentor, right?
Yeah.
I'm his official mentor, by the way. UC Merced is using our. I'm a mentor for a couple of other university assistant professors. So I think that when he joined that UC Merced, university supporting this, they can choosing an external mentor. So I was his mentor, but we haven't met, Well,
I think we met before the pandemic.
Yeah. And, so he's, if you're looking for the resume, basically the flyer is he got his PhD from University of Lyon. Lyon in Chinese. That's Lyon. Yeah, from France, and then spending some time at the NTU as a research fellow, and we are very actively working on AI. AI on IoT, wireless sensing. As you can see, this is a pretty cool technology. Can be applied to many other areas. So I think publication-wise has win quite a few best paper awards. Pick one example, 2015 Census Best Paper Award, and most recently, I think this year, congratulations, just win the ASM Career Award. So without further ado, welcome.
Thank you, Professor Shi, for this introduction. And I'm very glad to come here and talk with you guys and introduce my recent work. So today, I will introduce this arm tracking work, and it has been published in Census last year, and we are continuing working on this direction. So there are maybe more papers coming out. Let me first introduce what is arm tracking. And I'm tracking, I'm post tracking. We want to know the gestures of the arms. So when we track the gesture of the arms, the most important thing that we want to know is the wrist posture, the orientation of the wrist. So where orientation of the wrist, and then where is the location of the wrist. In the Earth coordinates, we call it global reference frame. Okay, so once we know these two numbers, and then because we also know the length of the arm, right? So we can calculate the location of the elbow. So we know everything about this gesture. So now we want to know the orientation and the location of the wrist. So suppose that we know it, what applications we can do? We can use we can ask the users just to wear two smartwatch to do some remote control for some motion game. We can monitor the fitness training of the user. One of the interesting applications that we are working on is healthy aging. So we are in California. So this is the Central Valley, and my group go to the Healthy Aging Association in Merced and in some nearby cities. And you see, this is fall risk fall prevention intervention class. So these elderly friends, they are exercising every 2 days to improve the balance of their body. So all the classes are offered by the Health Aging Association. It's an organization offer this class with very low fee. Okay, so but the problem of Health Aging Association is that when they offer this class, there are about 20 people there in a class. They only have one instructor, and this instructor is trained briefly, and all the instructors are volunteers, so they are not professional nurse or professional healthcare providers. Okay, so Health Aging Association, okay, we call it HAA. they ask us, computer scientists, to say, can you help us to improve the quality of the class for prevention intervention classes? And another thing is that they want to know the fall risk of all the participants and monitor the fall risk in a long time. So we are developing the arm tracking system. Once we know the arm, once we can track the arms of the user, right? So we can tell how good the users are doing their accesses. So we can provide a virtual assistant instructor to the user. So this is like a Siri or some virtual iRobot. Okay, it can tell you, oh, you are not raising your arm correctly, or you need to do something else. Okay, so this is a virtual assistant instructor we want to develop. Another thing is that we want to monitor the fall risk of elderly people at home. So you know that now we can measure the blood pressure at home, right? But 20 years ago, we can't do it at home. We need to go to the hospital and do the measurement. So our vision is that after 10 years with our technology, so elderly people, or we call older adults, they can monitor the fall risk at home and do it every day. So this data can be used by their physicians to monitor the fall risk and design some personalized fall risk prevention classes to them. So this is what we want to do. It's about smart health. Okay, so now let's see how can we track the arms by using smartwatches. Okay, as we know, smartwatches have some sensors like the accelerometer, gyroscope, and the compass, right? So do you guys know these two, okay? All these three sensors, actually, they measure the data in their own coordinates. We call it watch reference frame. So the smartwatch only knows its own acceleration and angular velocity in its own coordinates. It does not know what it means in the global reference frame. So our job is to translate this measurement to the global reference frame, so the smartwatch can know where it is, right? So let's see this demo system. Okay, as you see, this is the Earth. It's up, it is north, and this is east. Okay, this is our smartwatch. So our smartwatch also has its own coordinates, up, front, and right? So what is the orientation of the watch? It is the relationship between these two coordinates. Okay, once you know the relationship between these two coordinates, you know the orientation of this watch. For example, if you move the watch, now the watch looks like this, right? But if you move it, so this is orientation is changed. The relationship between this one and this one is changed. Okay, please note this one does not change at all. Anyway, okay, we assume that it does not, but actually it changed a little bit in different locations. For example, in California or Delaware. Okay, so now you know when we want to measure the orientation. So we want to know the relationship between the watch reference frame and the global reference frame. How can we do it? So the watch can measure its own acceleration and angular velocity and the north of the Earth, right? So we want to, based on the measurement of the watch, to know this rotation. Once you know the rotation, okay, you can rotate the watch reference frame to the global reference frame. Okay, so this is what we want to do. So the traditional method, what we can do, once you know the initial orientation. So suppose that you ask the user to stand, always start with this location and this direction. So you know this direction is facing north. Okay, suppose that this is north. Okay, so you know the initial orientation. So what we can do? We use a gyroscope's measurement to track the orientation, because the gyroscope measures the angular velocity of the watch's rotation, right? So you can, sorry, you can just integrate the gyroscope's measurement so that you can track the orientation at any time you want. But what is the problem of this method? You know, the gyroscope on the watch is very accurate, but it's not accurate as the gyroscope that we use in the airplane or in the rocket, right? Because it is low end, it's very cheap. So it has some errors. The measurement has some errors. So the errors can be accumulated during this interval operation, right? So if you just use this method, after like 10 minutes, the error will be huge, right? Because the error can be accumulated. So what do? We have some other methods that can help us. For example, in this work, the author found, okay, when the watch is static, means that the watch is not moving. So the accelerometer measures the gravity, because we don't have the arm movement, right? So the accelerometer only measures the gravity facing to the earth, right? So you see, this red arrow is the gravity. Okay, it's the measurement of the watch. This is what the watch measures in its own direction, coordinates. Okay, and this is the down direction of the watch's coordinate. Because the watch is static. Okay, so what we can do? So we know these angles between this one and this one. So we can rotate. We can rotate the watch or the phone to the gravity. So we know the relationship between the watch, this axis, and the gravity, right? So we know the relationship between the WIF, watch reference frame, and the global reference frame, at least in this direction. This is one direction. We also have another direction, is north. Is the measurement of the magnetometer. Magnetometer always pointing to the north of the Earth. So we know the angle of the phone with the Earth north. So we can rotate it. So once we know these two angles, we can know the relationship between the watch reference frame and the global reference frame. So we know the orientation of the watch, right? So we use these opportunistic moments to measure the watch orientation, and use this measurement to calibrate the orientations that we calculated by using gyroscope. Okay, so the result will be, the gyroscope's result, the arrow goes high, right? And at one moment, the watch is static, and we use the accelerometer and the magnetometer to measure the orientation, and then we just get the orientation error down to almost zero, and then we use the gyroscope again, and the error will increase again. And once we found that the watch is static, and then we use the accelerometer and the magnetometer again to calibrate the orientation results. Okay, and there is a recent work, it's a Mobicom 2018 paper. And they found actually the magnetometer can be used whenever you want, not just when the phone is static, right? Because the magnetometer always pointing to north. Okay, so they use a complementary filter to use the magnetometer's result to calibrate the gyroscope's results, always, okay? So what is the problem of the existing method? They are the rule-based method, means that they have some rules to combine all the measurements from different sensors together, right? It's based on some physical rules, but there are some noise in the sensors data. For example, the gravity, the accelerometer measures the gravity, right? But when the arm is moving, actually the accelerometer's measurement is not just the gravity, it's also the acceleration measured by the caused by the movement of the arm, right? So you see the gravity error is high especially when the watch is moving fast. And the magnetometer does not always point to north, because in the indoor environment we have so many metal structures, it will impact the magnetic field. So you see here the magnetic deviation is high, especially in indoor environment. Okay, and the sensors also have some inherent noise. So what do we want? What is the limitations of the existing method? Because they are based on some rules. Okay, even they use complementary filter or common filter. Okay, what is the problem? Problem is that all these data filter methods, they do not adapt to the noise level of the sensors. So what we want to do is to provide a more adaptive data fusion method that can change its setting according to the noise level of the sensors. Okay, so suppose that we can measure the orientation. Another thing for arm tracking is that we want to know the location of the watch. Okay, so that we can track the location of the watch. Okay, so we have some existing works. So what they do is that once you know the orientation of the watch, and you also know the acceleration of the watch, right? So you can track the location of the watch based on the acceleration and its orientation by using some Markov chain or some particle filter, some existing data filter method to fuse the orientation result and the acceleration of the watch. Okay, so what is the problem for this method? Anybody use particle filter? Anybody has some experience? Yeah, you have. So what is the limitations of particle filter?
Particle filter
Uh-huh.
can take time.
Yeah, it's very slow. Okay, and his particles. So in our experiment, we have 1,000 particles. It's not a big number. Okay, it's actually a small number. We only have 1,000 particles, and it takes like 10 minutes to get the result for one measurement. Okay, so it's time consuming to run the particle filter. Okay, so what do we want? We want a real-time and accurate location tracking system. Okay, first it can provide a real-time result. Another one is more accurate. Why we see that accurate? The existing work is not so accurate. Okay, why? Because all the existing work is orientation based. So you use the orientation result and the acceleration measurement to calculate the location, right? So what is the problem? Problem is that when you have the orientation result, if the orientation is not so accurate, the errors in orientation will transfer to the location, right? Because you use inaccurate orientation to calculate the location. So of course, the location result will not be accurate. Okay, so this is the limitations of the existing orientation estimation and location estimation, right? Okay, so what do? We provide a real-time arm tracking system. So what do? We use deep learning. Okay, we have the multitask learning. We developed a neural network architecture so that it takes the measurement from the IMU sensors, all these 3 IMU sensors all together. And we have this multitask learning model, so it can get the results of the orientation and the location together. So the location results is not based on the orientation results. Okay, so they just learn together. And we also have an attention module. Attention module assigns different weights to different IMU sensors. If we found, for example, at one moment, if we found accelerometer is good, we will assign a high weight to accelerometer. And later, if we found the gyroscope is better, and then we assign a high weight to gyroscope. So this attention module can adjust the weight to different sensors. So it can be adaptive, right? So now, suppose that we have this deep learning model, okay? You have the full IMU sensor measurement, and you can get the orientation and location tracking results. So if you are the author of this system, okay, so do you guys know what is missing in this design? Right, you have the watch measurements, and then you have this deep learning model. It can tell you the orientation and location of the watch. So what are we missing here?
Also,
Sorry, say again.
the output
The output is orientation and location tracking.
runners. That runners.
Yes. We need, this is a deep learning, okay? Whenever you talk about deep learning, you need the label data to train the model, right? So what is the ground truth of the orientation and location? So that you can collect the sensor data and the label data to train the model. Okay, so where are the ground truths? So we developed a system, very cheap system to collect the label data easily. We use this is a Meta Quest, okay? And it's a VR system. And use this VR system, we can get the orientation and location of this watch easily. And based on this system, we can get the label data to train our deep learning model. Okay, once we get this trained model, we don't need the label data again, right? So this model has already been trained, so that you can use this trained model to get the results. Okay, so the label data system is only used to train the model. Once the model is trained, you can use the watch freely without the label data collection system. Okay, let me briefly introduce all these different tasks. Okay, so what we have learned during this design process. So first, the multitask learning. We learn the orientation and location together. Okay, so that the location result is not based on the orientation result. Okay, so we have RNN LSTM bidirectional LSTM model, and for each sensor. And then we combine all the sensors together and go through a fully connected layer for orientation and location together. So as you see here, in this structure, we first process the sensors data together, okay, within this model. And then use the extracted feature for orientation and location independently. Okay, so we will see that this actually can improve the orientation and location measurement results. We also have the attention mechanism. So this is the measurement for different sensors. This is gyroscope, this is accelerometer, and this is gyroscope and magnetometer. Okay, and the different sensors has different weight to the final results at different time. Okay, so we can learn this weight automatically and based on the measurement. For every time, okay, we know once we receive the raw measurement data, and based on the data, we can assign a weight automatically. Of course, this attention module is trained offline. Once it is trained, it can assign the weight to the sensor data in real time. Okay. So this is the architecture. So now let's see how can we get the label data. So what we want to know, the label data is the orientation and location of the watch, right? So what we can do to get the label data? You can use a KNAP, right? My student tried KNAP. It's very accurate to track the location, but the problem is orientation. It cannot know the orientation of the watch. Okay, and you can also use the camera system. For example, in this room, you have like more than 8 cameras around it. So the camera system can get the skeleton of the user very accurately. But the problem is that it's very expensive. And another one is room dependent. So you have the camera system in this room, you can only do the experiment in this room, right? You cannot do it in the hallway, right? But for the deep learning model, we need to collect label data everywhere. If you want to use the system here, you need to collect training data here. If you want to use the system at another place, you need to collect training data at that place. Okay, so we cannot move this camera system easily to some other places. So that's why my students found MetaQuest. It's very accurate. The orientation error is less than 1 degree, and the location error is less than 0.7 centimeters. Okay, and suppose that you have this VR controller. This VR controller can measure its own orientation and location anytime, okay, accurately. And what we want to know is the orientation and the location of the watch, not the controller. But what we know is only the result of the controller. We don't know the watch label. So another question that we need to answer is, how can we translate the result of the controller to the watch label data? Right? So this is two translations. First, we need to fix this relationship. So my student just used some sticks to fix the controller and the watch so that their relationship does not change. Okay, and now the problem is that how can we use the controller's orientation to know the watch's orientation? We need to do some transformation. Okay, so this is orientation is just a matching, a rotation matching. Okay, so this is the orientation or the rotation matching between the watch and the VR system, and this is the rotation matching between the watch and the controller. And that one is the controller and the VR system. You know, this one is measured by the VR system. Okay, and let me show you. What we need to know is a watch and the VR system, right? Watch and the VR system. And what we know is that this relationship is fixed because it is fixed by the sticks. Okay, so this one is fixed. The rotation matrix between the watch and the controller. And the TCV is the controller orientation in the VR system, So this is the measurement of the VR system. We also know. So we know this one, and we want to know this one. But we also know this one is constant, right? So now the problem is that we want to know this constant matching. Okay, so it's like AX equals Y. We want to know A. this coefficient, right? So let me ask you guys a question. If you have an equation ax equals y, you want to know a, what you can do? You have some measurement of x. At the same time, you have some measurement of y. You have some pairs, right? For example, x0, y0, x1, y1. Then you can calculate the coefficient, right? So what we want to know is exactly, we want to know some measurement of the watch's orientation and their corresponding measurement in the VR system. Fortunately, we know it. Why? Because we know when the watch is static, the watch can measure its orientation accurately using the accelerometer and the gyroscope. So the watch knows its own orientation in the global frame when it is static. And the VR system also knows its own orientation in the global reference frame. Okay, so based on this observation, we know some pairs of the measurements, right? We know that when the watch is static, we can measure the watch's orientation very, very accurately in the global frame. And at the same time, the VR system knows its own orientation in the global frame. So we can have some pairs. So we know we can calculate the coefficient, the rotation metric. I'll skip the mathematic details, okay? So another thing is that we know the location of the controller, right? We want to know the location of the watch. It's also a problem. Why? Because we know the location of the watch is always in the middle of the watch, but we actually don't know what is the center point of the controller. Again, we want to know the relationship between the location of the watch and the location of the controller, right? Again, if we have some measurement at some time points, we know the location of the watch and then the controller's location. So we can have some pairs. So we can calculate the relationship between them, right? But the problem is that at any time, we only know the location of the watch, but we don't know actually where is exactly the location of the controller. So what do? We design a very simple experiment. We fix the location of the watch, and then this controller, right? So it rotates around the watch. We make sure that the watch does not move at all. Okay, so we can have this circle. This circle is the controller's location. And based on this circle, actually, we know the relationship between the controller's location and the smartwatch location on this plane. Okay, on this plane. And we do this experiment on another two planes so that we can know this relationship. Okay, now we have the label data. And we have the design system. So we implemented on the smartwatch, or we use some database and also the Android Studios to implement the deep learning method. Okay, and the VR system, we developed the data collection system. And this is the experiment that we do to collect the label data. And okay, we evaluate the system by using one watch and one VR system, and we implement the system in different in Python and TensorFlow. And we do the experiment in two different places. One is in the conference room, and another one in the hallway. We have 9 volunteers to collect the sensor data. and we compared our results with some existing work. And we do the experiment to evaluate our system to compare our accuracy in orientation and location with the existing works. And we also study what is the performance gain provided by different components in our design. And finally, we also evaluate the overhead of our system because we want to run our system on the smartphone and smartwatch. Okay, so let me show you some overall performance results. As you see, this is the room, and this is our orientation error. This is an existing work. This existing work also uses deep learning method and Kalman filter, traditional method. We combine these two to do the orientation estimation. As we see, we can reduce the orientation error by 20% compared with the existing work. And how about the location error? You see, we can reduce the location error of the state of the art by almost 47%. Okay, let's see a demo. The blue curve is ground truth. This is what we get using our smartwatch. Okay, please note, when the user uses it, the user do not need to wear the VR system, okay? We do the demo use the VR system because we want to draw the ground truth. But actually, when you use it, you don't need to wear it. You just wear a smartwatch. It knows, it can track you like this.
When you use it, you don't even need this the front.
No, you don't need the controller.
Just the watch.
Yeah, just the watch using.
Then we can buy it anywhere.
Yes, yes.
This is great because one of our faculty members, so she gets the best paper award in the chase this year. The work is doing using this guy, this. Seems
yes.
Your approach, you can replace this completely. Just need this for training purpose.
Yes, and we have the same goal in smart health.
Yeah.
We want to use it in the health agent association to help the older adults to monitor its fall risk every day. Yeah. But I will show you that it also has some limitations. So we have some following up works. But I will ask you guys again later. Okay. So let's see another demo. So in this demo, the watch measures the IMU sensor data and it transmits the raw data to a smartphone. And the smartphone will run our deep learning model and get the result immediately. So the users do not need to transmit its own raw data to the server. The user can keep its own data privately if she has a phone. Okay. And we also show that although it is a deep learning model, it's RNN and it's a multitasking learning model, but still it can run on a smartwatch, in a smartphone. Okay.
Or you can run it, but then after you run this, for how long you can use all the power?
Yeah, very good question. So now IMU needed to smartwatch need to transmit the raw data to the smartphone. We tested this 1 hour. Yeah. Let me conclude this work. And we provide a 3D arm tracking system, and it is more accurate and can provide a real-time result by using deep learning. Okay, and to use the deep learning techniques in the mobile computing and the smart health domain, we need to collect the ground truth data. So we have a ground truth data collection system, and we do the experiment to validate it. Okay, we have already released the data set, the IMU sensor data and also our label data. So if you are interested, you can download the data and try. Yeah.
So you mentioned the old way to collect the ground truth data.
ground truth data is room dependent.
Yes.
So you only have to test the multiple locations.
Yes, we tested in 2 locations. One in the hallway, one in the top.
And is your method the people dependent?
Very good question. We have non-volunteers in this work, and we use 5 users' data to train our model, and we tested the model on 4 other new users, and the performance will go down slightly. Yeah. Why? Because different users have different height and different movement. So in this work, we are the first one, I think. We ask the user move freely. They can do whatever they want to move their arms. But in some other works, especially gesture recognition, they always ask the user to do some predefined movement, right? For example, circle, push, and pull, and some predefined gesture. But in this work, we do freely. So that's why our system, the performance goes down slightly on new users. Yeah.
So, since the model is running on the smartphone, I'm curious how much energy consumed for the smartphone battery.
Yeah, a very good question. I have some backup slides. Okay. I will introduce this some ongoing work on my lab later, but let me first show you some the power consumption. Okay, this is the power consumption. So if you use your phone to play music, the power consumption looks like this. This is idle. Okay, this is idle. And if you use our system to run our system for inference, okay, the power consumption is this. It's comparable or even less than playing music. Because we use TensorFlow Lite, actually the model is very light. And the inference, the inference is very fast, okay, it's several milliseconds to do one inference.
And this is the energy for one inference.
No, this is sorry, it should be power consumption. It's not energy, no, because this is time. This is the power. We measure the current. Okay, so this is the power consumption. This is.
So do you know that the real word to be used here is called power dissipation, energy consumption. So you never have a power consumption. I know many people using power consumption. Power is not consumed. Power is an instant value. So in this the area is called power dissipation. So
Dissipation, yeah.
Dissipation, because it's an infinite value, and then you can say energy is sort of like the area.
Yes, exactly. Yeah. Yeah. Thank you. Yes.
New Apple Watches, they have they can detect heart crashes and they'll send the data to emergency contact. So the Apple Watches, they use a similar technique or different?
Sorry, say again.
The Apple Watches, it has it can detect heart fall. And it will send the location and other steps to an emergency contact number. So, does it
Yeah, very good question. So our system was designed, okay. So fall detection has been studied for decades.
Yeah.
Okay, we have different systems to measure the fall. If a user falls, okay, so we can use the Wi-Fi signal to measure whether the user falls. If a fall happens, we can call the emergency, and we know the location of the user. So, yeah, this has been done for many years. So this work, we have a vision is that beyond the fall detection, we want to do fall prevention. Before fall happens, we want to measure what is the risk of a user to fall in the near future. So we measure the balance of the user. whether these two arms are balancing, the two legs are balancing, so that we can infer the fall risk of the user. And our goal is to measure the fall risk at home. So the users can know its fall risk every day and monitor its fall risk in the long term. And yeah, thank you.
I have a question about loss function design.
Yeah.
This is a multitask training process.
Mm-hmm.
So I think you actually have two heads.
Mhm.
Right? So finally, how do you tune the weights of the tasks?
Oh yeah, very good question. It is one part of the hyperparameter tuning. And first, we need to normalize orientation and location results. Normalize it and change it to 0 to 1. And then we try different weights to and then find the best result. Yeah. Another questions? Can I ask you guys a question? Yeah, please.
Questions. May I ask what kind of the library or tool you measure the power?
The library, we use a monsoon monitor. You know, it's a hardware you connect you connect to your phone's battery, so we can measure the power consumption of the phone directly. It's a hardware.
So for training purpose, you will use deep neural network, right?
For training, we use deep neural network.
Also, have you used like any specific model, like convolutional neural network model, or like I'm trying to say, can we integrate transfer learning or pre-trained model for training purpose?
Yeah, very good question. So that's what a question that I would like you guys. So what is the limitations of this work? If you work on this project, what is the next idea?
Training is like very time consuming.
Yeah, the training is very time consuming. You know, we ask non-users, volunteers, and every user needs to collect more than 1 hour data for us. So I really appreciate our volunteers because they need to wear the VR system and do this for 1 hour.
Well, that's a lot of work.
Yeah.
Get by this.
So this is one limitation of this work. Once you use deep learning, you have to collect the training data. So the training process needs a lot of data. We try to reduce the training data requirement of this work. Yeah. Do you think another one you mentioned about transfer learning, right? So this work, if we train a model in this room and we want to use this model in another room, actually we encounter some problems because the model trained in this room only knows the data distribution of this room, especially the magnetic distribution. Because the magnetic field is highly distorted in the indoor environment. For example, all the different furnitures in this room, it will have a different magnetic field in this room and in another room. So if we train a model, a deep learning model in this room, actually, if we use it in another room, the performance is go down sharply. So we need a transfer learning, so that once we train a model in this room, how can we transfer the model to another room with less training data in the new room?
You can transfer just the weight of the model of this room.
Yes. So that's what we are working on. Yeah. Okay.
I have one question. So, do you consider the Gaussian networks to output the distribution so we can sample from the distribution to counter the noises? So for now, I guess you use a deterministic, you just output one value. But so for example, I guess maybe this will help. Yeah.
Very good point. Okay. My student is trying this idea in another project. It's not this project. Yeah, I would like to talk with you about this idea.
They're all my students, so in the afternoon you will have chance.
Yeah, we are using Gaussian process in building energy control. because we found Gaussian process is very powerful. It can provide you the confidence of your output. And based on this confidence, we can do more reliable, we see safe control of the energy in the building. Yeah, very good point. Yes. Yeah. Okay, so let me go back to my talk to wrap up my talk very quickly. So this work is deep learning based data processing, and we also have some traditional data processing method like a particle filter, complementary filter, right? All these different data fusion methods. So what is the limitations of the traditional method? It is a complex system model. It always needs a complex system model, but sometimes we don't have this complex system model. Okay. Another thing is that because it is rule-based, right? So it does not adapt to the environment very well. But what is the limitation of the deep learning method? It needs a large training data set, right? And it does not scale to the new places. So what we want to do is that we want to combine the benefit of these two systems and avoid the limitations of these two systems. Okay. So that's what we are working on. Domain knowledge enhanced deep learning to solve some specific domain specific problems. Okay. Let me show you some examples. So for example, the arm tracking. We are still working on this problem. We found that you ask a deep learning model to learn the orientation and location directly from the raw data. It's very hard. So we need to train the model with a lot of training data. So we ask ourselves a question. Can we ask the deep learning to do a simpler job so that we don't need such large training data set, right? So that's what we are working on. We combine the traditional method, particle filter, complementary filter, and the deep learning method, and to provide a lightweight deep learning model for orientation estimation. And to conquer the limitations of deep learning, we also do some representation learning to process the data more efficiently, so that we can learn from the new presentation of the raw data more efficiently. Okay, another one is transfer learning. Okay, so this figure can summarize the work in my lab. So what we are working on is to develop different IoT systems for California's carbon neutrality goal in 2045. So in California, so it were expected to achieve that zero greenhouse gas emission in 2045. Okay, this is a very big promise. Okay, but it is very hard to achieve. So what we are doing is in 3 domains. First is we develop new deep reinforcement learning models to control for the smart building control. So we control the HVAC system, the air conditioning system, and the ventilation system in the buildings, so that we can save the energy of the buildings. Okay, so we also deploy sensors in the orchards that we can enable smart irrigation system. So based on the soil moisture level of the measured by the sensors, we can do better control of the irrigation system so that we can save water. So we also have some works on this domain. Finally, is the fundamental research is the data collection and the transmission system. So we developed the LoRa networking systems deployed in the field, in the buildings, and in the farms, so that we can collect the data and also send the data back to the system efficiently. So this is what we are working on. For example, let me show you some pictures. So my students deploy the sensors in almond. This is almond orchard, and we deploy the LoRa system in the orchards to collect the soil moisture sensor data. Okay, so this is the LoRa gateway. We have that we can collect the data from all the sensors deployed in the on the ground. Okay.
What's the range of the LoRa network you have now?
Okay, very good question. So theoretically, it can reach multiple miles,
Yeah,
but it is in free space.
yeah.
But if you deploy we normally measure the soil moisture, it's underground.
Yeah.
And we have some, we can have the antennas on the surface. So then the signal needs to traverse the canopy of the trees to reach the gateway. And the wireless communication distance is highly impacted by the leaves by several times. Okay, so what we can measure, based on our measurement, it's only like several hundred meters, and the signal is not reliable. And we can receive the packet, but in the packet we have some error bits in the packets. So that's what we are working on. So first, we want to know how the wireless signal propagate in the farm. We have the signal propagation models, and we also have some channel coding method, so that before we transmit the data, we code the data by using some channel coding method, so that once the gateway receives the data, even there are some errors, we can correct these errors based on our channel coding method. So this is about LoRa networking. Okay, yeah, that's all. Thank you, guys.